Hello, my name is Sergey, and today I'd like to talk about building huge monolith applications with Maven. So today you will learn why your multi-module Maven builds can be slow, why the parallelism is not easily scalable as you may expect, and how we can solve those problems and stay on Maven. So I work at Miro, and at Miro we do online whiteboard for collaborations. Most of our code is microservices, about 200, but the central backend application is 2 million lines of code and 1,000 Maven modules. Let's try to build this. So how we usually do it? Something like Maven clean verify. So in this scenario, it will compile our Java code, compile tests, run unit tests. Integration tests are not included by default. So what time we will have there? In our case, something about 41 minutes. So can we make it better and faster? So by default, Maven is using only one worker thread. And if you want to use more worker threads, you need to specify it on the command line. There is a special parameter called -t threads, which you can specify on the CLI. Or if you want to use this as default, you can define it in a file called .mbn maven config, and it will be used by default in your builds. So instead of one default worker, we now build with 5 workers, but our build time is only twice faster, 21 minutes. And this can be a bit confusing because we can anticipate more, better boosts. So my laptop has 12 cores, so I can try to use more workers. I can specify the number as -t12, or also I can use a multiplicator constant called C, which is a dynamic value of your local course number. But surprisingly, build time is still the same, 21 minutes, the same as 5 workers. And this can be confusing. Why it happens? So to investigate this, we need to add some observability tooling. For example, we can add the velocity Maven extension. So it's easy to do. In MVN extension 6ml, we just add the block declaring this extension and the configuration file. And let's try our build again. What I'd like to focus attention on in this scenario, we intentionally disable build caching to see the worst possible scenario when all our build tasks is executed to inspect bottlenecks. So you can see that our workers on the timeline that goes from left to right are loaded unevenly. So for example, during this interval, all our workers are busy, and it's quite correlates with CPU load. So our system resources are utilized quite well. But there are several modules that are actually bottlenecks because Maven executes only one module at a time. And let's try to understand why this happens. If for some reason you cannot use the velocity Maven extension, for example, for security or whatever, there is alternative timeline builder solution which allows you to build your timeline locally. It doesn't have any other build scan information, but also can represent how tasks are distributed between workers during your build. So long story short, your modularization of your multi-module application is a crucial factor which actually defines how good your build is parallelized. Maven can build modules in parallel, but only those that don't depend on each other. So if we build a dependency graph, we're talking about modules that exist in the parallel branches of those dependencies, and Maven can build them in parallel. So let's look on a bigger scale how Maven Reactor works. For any module which is a part of our build, there is the same rule. before starting building our module, it resolves all dependencies. That's called upstream dependencies. This can be libraries that are downloaded from the registry or other modules. And for those modules we depend on, despite the scope, compile, runtime, or tests, it doesn't matter, we will wait for all phases, all goals of those modules to be built before we can start our building our module. Then it happens again for our module. Now, when all dependencies are resolved, we will build all phases. So, for example, if we run clean install, it will run clean, compile, running tests, packaging, integration test, install. And only when all those phases and goals are finished, our module will become available as a dependency for downstream dependencies who depend on us. And they will start building their and Maven will start building them. So let's consider an example of a multi-module project that contains 3 modules like test utils, core, and app, and try to build it with a classic Maven clean package T5. So let's try to build our multi-module build in parallel. So we will not have any parallelism there, because first Maven will build our test utils, then it will build core, all the phases, and then it will build up, because those modules depend on each other. There is no parallelism, even despite there is a multi-module application. Even if your project has 1,000 of modules, you shouldn't expect that it can evenly load your workers. Because probably you will have some modules that accumulate too much source code, or too long tests, or they have too many dependencies, or too many other modules depend on them. And those modules will become bottlenecks. So actually, all those white spaces is unloaded CPU cores. There is some correlation for sure. It's not the same. I mean, workers and CPU cores are not the same, but there is strong correlation between them. So you can see that, for example, here CPU is loaded quite well, but there is a lot of white spaces. So our system potentially can do better. So some historical context. So Maven was introduced more than 20 years ago, when we had only single core CPUs, and it got parallel build support only on the 3rd generation. So, and when it was introduced, Maven authors had to preserve some kind of back compatibility and not to break their builds. This is why the build graph that is executed during the build is using modules as nodes of this build graph, not the phases or plugin goals. So if we compare this, for example, with Gradle, its build is way more granular, because in Gradle, tasks depend on each other and it utilizes multi-core CPUs much better. But Gradle was introduced significantly later than Maven, and the author of Gradle were aware that multi-core systems is a standard at this moment. So there are a few things that we can do. I think one of the most efficient ways is split large modules to smaller, which will also allow to remove redundant dependencies. You can extract code generation to libraries if it's possible, stop deploying redundant artifacts, use Maven profiles, and define more steps as optional. Also, this quite working advices use latest GDK, because newer version GDK has faster runtimes and faster compiler. And if you use Kotlin in your codebase, also update to Kotlin 2nd generation, because it's fully rewritten compiler. And for example, Kotlin 2.2 introduces Kotlin daemon, which is quite efficient for this. Last year, I talked about all those things, so you can find my presentation online. All those points are still relevant. Today, I don't want to repeat myself and go to the next chapter of this research. And what I'd like to talk about is, let's revisit standard behavior of Maven. So what we can do. Let's check the timeline of some particular module. Usually, running tests, and especially integration tests, takes much more time than compilation and compiling tests. So the idea is simple. By default, package phase, which is responsible for assembling jar from your compiled classes, goes right after tests. Let's move it before compiling tests, but after compiling. I will now explain why do we need this weird trick. In combination with the second optimization, what we can do, instead of waiting all phases to be executed to run all downstream dependencies, now we can run downstream dependency build exactly when the package phase is over. So we can also call this optimistic strategy. So by default, Maven uses pessimistic strategy, assuming that tests may fail. Instead, we will run tests in parallel with downstream dependencies. For sure, if test execution of this module will fail, the overall build will fail. But what you can see now, we load our CPU cores way more efficiently, and this, in average, will be way faster on the multi-core systems. So, the question, how we can implement this? The good news is that we don't need to fork Maven. Maven APIs are quite flexible, and there is a conception of so-called extensions. They are like plugins, but work on a lower level. And you can redefine even basic functionality there. There is a crucial interface which is called Builder, which is responsible for building multi-module applications. And standard implementation of this builder is called multi-threaded builder. So you can find the source code in Maven and inspect how it works. Despite the fact that its internal API it's quite stable since it was introduced in Maven 3. So what we can do, use this multi-threaded builder as a reference example and implement our own builder. So during this research, the project called Maven Turbo Builder was created and published on GitHub with as an open source, licenses under Apache license, and the builds are available in Maven Central. So it's easy to connect to your projects. Just define it MVN extension 6ML, and also you need to define parameter which is called builder. So the comment will now look like Maven clean verify T1C B turbo, and it will switch from default builder to this turbo builder. Also, you can do this default builder the same. You need to define it in MVN Maven config. So engineers that are building their projects locally or in CI/CD will use this behavior by default. For example, we use this configuration at Miro for a few months and it works quite well. So let's build our monolith server again. Just a reminder how our timeline diagram was looking before and now how it looks now. This is the same project. There are only two differences. This is using the standard Maven Builder, and this is using Turbo Builder. This has 11 or 12 threads, and this has only 7 threads, workers. We don't need more workers here because it fully utilizes our CPU already. And increasing number of workers here does not speed up our build. I tried this on different projects at Miro, also building like open source projects. So boost is different, it depends on the particular projects, but in many cases the average boost is around 30%. Also, the implementation of this builder uses API that are quite stable, and so it has a very good compatibility with most of Maven 3 versions. Also, the latest Maven 4 release candidates work with it. All standard plugins like Surefire, FileSafe, and other standards plugins are working pretty fine. And classic things which are used quite often like Spring Boot, Uber, Jar, Repackager also support this custom behavior. It also supports classic Maven features like building subset of modules, skipping test compilation or running tests, resuming from failed model, etc. So it's quite compatible with standard Maven build. Also, it's compatible with Maven daemon. The only difference that you need to specify instead of -b, you need to use another parameter name. I've submitted an issue to Maven daemon because I think -b also should be working, but whatever, it works with Maven daemon as well. Another good news is that this is compatible and complementary with build cache solutions. So let's run our build again, but now we do not disable the velocity build cache. And the build time, instead of 20 minutes, should be only 2 minutes. Because we have some tasks that are not friendly with caching. For smaller projects like Guava or Drop Wizard, the build time is less than 50 seconds. So it's quite good. For sure, there are some issues with possible issues, and one of the problem is so-called test jar dependency. So if you don't know test jar dependency, the way to declare dependency to src test of other module. I'd like to strongly recommend not to do this, but also this is possible using Maven Turbo Builder, just the optimization is a bit smaller here. When you increase the parallelization of your build, one of the problems that will probably happen is tests conflicting each other. So that wasn't happening before. Especially this problem can affect your integration tests. So for example, if you start a web server in a Spring integration tests, instead of fixed port, which is defined port, you should use random ports. You can access them in your test with this annotation. Same, if you create manually your server sockets, instead of fixed server socket number, you can use port 0, which will assign available port. If you use test containers, you should also use dynamic ports, which is best practices of using test containers. You may ask, why just not to run tests in parallel? Indeed, for many projects, especially which have only unit tests, this can work quite well. But also this can lead to spikes and uneven distribution of the load. Also, for example, in Spring integration testing, this will lead to repeated initialization of the same context, because Spring test has a cache of context that is reused, but it has a scope of the thread. If you run your tests in several threads, it will have to initialize and start the context several times, and this may lead to losing performance. Can this be a part of Maven? First, Maven 4 will be released quite soon, so it's too late to consider this as a possible option. But I hope this optimization can be a subject of discussion with, for Maven 5. What I'd like to emphasize here, this change breaks compatibility. But, for example, Gradle is a good example of the tool that deprecates and then removes some old patterns that are not relevant anymore, and it allows Gradle to evolve faster and get rid of old problems. So I believe for Maven we can have a consensus here, and in theory revisit this original design, which is not relevant after 20 years. One more thing that I would like to pay attention to. In the internet you can find advices like how to scale my build. Use T2C, T10C, I mean use many threads. Don't do this because there is a limitation that I just explained of the parallelization. Usually you don't need to use more than T1C, more than number of your cores. Just keep in mind that, for example, on such laptops, only half of the CPU cores are actually powerful CPU cores. The second half is power efficient CPU cores. Also, you can learn the Amdahl's law, that is a theoretical explanation of limited scalability of concurrent applications. And from my personal experience, which is very similar for Maven builds and Gradle builds, the most efficient number of cores is around half of the cores. So your experience may be different, but it's less than number of CPU cores. And you will have the maximum possible speed of your builds. And I recommend you to use smaller amount because it will also reduce the average consumption of your memory, load and disk, etc. Because your system has three capacity: the CPU, memory, and disk. And with a higher contention of those resources, instead of boost, you can have degradation. Just one more advice. If you have issues building your projects locally, same for Maven and Gradle, open Activity Monitor, the CPU page, and especially the memory page. There is a very interesting indicator which is called memory pressure. Even if you have 64 gigabytes, but run a lot of Docker containers, a lot of Chrome tabs, IDEs, databases, whatever, eventually your system can start swapping. And instead of building faster, your system will have a degradation. So especially on a higher number of working threads. So pay attention to this very informative monitoring. Also, if we're talking about building large projects, there are crucial performance factors. It's a build caching, test distribution, and selective test execution. But again, you need to optimize the average and the worst case when you need to run all your tests or build cache entries are not available according to your change. But it should be complementary to those three factors. And to summarize, the main factor is modularization. Split your large modules to smaller modules. It will boost your build. It will define better boundaries of your domains, better APIs, better code ownership. So the second is, don't define too many workers. Limit them. Instead of increasing number of workers, try to leverage as maximum as possible the minimized number, because in overall the performance of your build will be better. Use proper tooling to inspect bottlenecks like Velocity extension or Takari. Build cache is a king. It's a huge major boost, but don't just rely on it. As mentioned, it should be complementary. And if you're working at a large scale, if you have hundreds of modules, maybe thousands of modules, be ready to revisit standard behavior. I think this is normal, especially if you want to stay on Maven instead of changing the build tool. Feel free to try the Maven Turbo Builder. Also, the presentation slides can be found on the internet. So that's it.